Hi, I'm Ariel McDermott.
My name is Maxim.
We're two fourth-year students at Heriot-Watt University, and this is a part of our Communication Devices and Systems course. So what we're going to be doing today is designing, manufacturing and testing a square patch antenna for communication applications.
The base parts of our antenna are a lambda by 2 resonator, lambda by 4 quarter wave line, and a 50 ohm line, and this is how schematically it looks like our antenna. We will compute our values by using a MATLAB code, which we're writing down, and we will use our FR4 substrate material for this antenna, and this is values which we will get from the MATLAB code. Now we will model following schematic in the ADS. In order to do that, first of all, we assign our substrate, and then we're putting our 3 microstrip lines, which are representing our base schematics. We're obviously writing down our values obtained from the MATLAB. Now we need to generate our layout. This is how our antenna looks like in the layout window. In order to simulate our schematic, we need to first assign the substrate and then assign a frequency plan in order to see what's going on our frequency and how will we approximate our values. So from our results, we can see that we have a small frequency shift to the right. We also can see that our S11 is minus 7.3 decibels. We improve our results by changing our values of our wave transformer and the lambda by 2 resonator. Let us see how in 3D our antenna will looks like. From the ADS, we can also see how our right antenna radiating. By choosing our resonating frequency, we can see how our current radiating on our antenna. We can also see how our antenna radiates. By choosing our 3D plot, we can observe that we have a linear polarization of our antenna. This is how it looks like in the ADS. We can also display our antenna parameters. And as it follows, we have our decibel gain, we have directivity of 6.2, and we have efficiency around 37%. Which is quite okay for the FR4 material. Let us improve our matching. In order to improve matching, we will change our width of our quarter wave transformer and change the length of our lambda by 2 in order to get some frequency shift to the left as we want. From the results, we can see that we have our design frequency as we wanted. We can also see that our matching is approved to minus 20 dB. So we're quite happy with our result. So let us union our structure so we can submit our DXF file and finally produce our antenna.
So here we're using a small USB pocket VNA to measure the antenna. So this is a one-port device that we've got, patch antenna, so we need to do a calibration for an open, short and load. There's no need to worry about the through calibration. So I'm going to do that just now, and then we'll display the results of the S11 reflection coefficient once I'm done. So we've calibrated the VNA and connected the antenna to it and run an analysis for the S11 parameter. So we can see that the frequency has shifted downwards slightly, so it's now matched to a frequency of approximately 2.43 gigahertz. What we can also see though is that we have good transmission at this frequency, as the power loss reflected back from the port is minimal. We have a power level of minus 20 dB at the frequency. So now we're going to perform the same measurements but with a higher spec VNA. So we've got an Agilent VNA just here. So I'm going to first calibrate it once again using the same method with an open, short and load ends. So this here is an APC 3.5 female connector. I'm just going to be following the calibration wizard to get this set up. So firstly I'm going to connect the open end. I don't have a torque spanner with me, but I'm just going to tighten up the connectors a little bit. Okay, now repeat the same thing for the short. And finally for the load. Okay. So now we're going to connect up our 2.5 gigahertz patch antenna and have a look to see what we get for the reflection coefficient, the S11 parameter. Okay, so I'm just going to hold this up slightly as well. So we've connected up the antenna and we are now observing the S11, so the reflection coefficient of the antenna. So as we can see by placing a marker, we have a dip at minus 22 dB at 2.429 gigahertz. So the antenna was designed for 2.5 gigahertz, so we can see that there's been a slight downward shift in the frequency, and this could be as a result of errors in the simulation process and in the fabrication process. We've also got a lossy substrate and
So we can actually see the difference between two different VNAs. This is just a simple pocket VNA, and this is much more sophisticated and expensive vector network analyzer. And as you can see, the much better results most likely will give this VNA. As we can see, we designed on 2.5 gigahertz. However, it's slightly shifted. We can use our experience in the future, such as developing much more sophisticated antennas. Also, we use the following antenna on our next laboratories, such as using those two antennas and transmitting different information. And this will conclude our laboratory for now. Thank you very much for your attention, and see you next time.